Well, hello and welcome to week 5 of Instrumentation and Measurement in ME397. Last week we introduced the concept of strain gauges as a measurement system, and this week we're going to continue on with that, discussing how we can use multiple strain gauges to compensate for unwanted effects in strain and stress measurement. We're also going to tie into that digital data acquisition using a computer ADC, analog to digital conversion board, and LabVIEW software. We're doing this because your next assignment is going to involve creating your own Wheatstone bridge to measure a strain from a strain gauge, and you're going to measure that voltage using your LabVIEW program through your computer DAC system. So first, let's look at strain gauge systems. Let's focus right up here at this image of a Wheatstone bridge first. And let's recall last week where we derived the relationship between voltage and resistance for the Wheatstone bridge. Remember that we have to use the Wheatstone bridge because a strain gauge would experience a resistance change on the order of maybe a few thousandths of an ohm, or 10,000ths even rather. Well, the problem is that a digital multimeter is not going to be able to accurately resolve a resistance change that's small. So instead we have to seek another way to transduce or to change that resistance change into something else that can be measurable. And the Wheatstone bridge allows us to do just that. It allows us to take a small resistance change and convert or transduce that into a larger, more measurable voltage change. So we spent some time last week deriving this relationship, and I'll draw your focus here to this first equation, which was a result of the Wheatstone bridge looking just like two parallel voltage divider circuits. And you learned all about those in probably physics and then also the electrical engineering circuits classes you've taken. But we have that the output voltage measured here on the signal corners is a function of the input voltage provided by some sort of power supply source, as well as the ratio of resistances, the four resistances in the four arms of the bridge circuit. Okay. So here's our Wheatstone bridge just sitting normal as it is. And we can replace the different arms with strain gauges in lieu of a normal resistor. So why would we want to use multiple gauges? Well, let's first work through the relationships here and look at the math, and maybe that will inform us as to some of the usefulness here. For the most complicated case, we're going to assume that there are 4 gauges and that each gauge changes by some small amount. So each gauge is strained, and therefore its initial resistance is going to change to that initial resistance plus some change in resistance. So for each of the 4 resistors, we will assume that they become strain gauges experiencing some strain resulting in a resistance change, and we will insert those, replace them for the 4 resistances in the voltage equation. So now I have my output voltage as a function of my input voltage, and for each of the 4 resistors now I have their base value plus the small change in each one. And if I want to find the change in output voltage in the strain case, I'm essentially taking this output voltage after the strain minus this output voltage before the strain occurred. And in doing that, I have this entire quantity minus this entire quantity. Then I have minus this entire quantity minus this quantity. So you can see the long equation here. Continuing along, I realized that I can use the gauge factor definition for a strain gauge to relate the change in resistance to the strain that I'm seeking to measure. Remember that the gauge factor is just the sensitivity of the strain gauge as a transducer. It's turning a change in length divided by length, or in other words a strain, into a change in resistance divided by resistance. So here's my strain on the denominator and my output or resistance change in the numerator. And that ratio is equal to the gauge factor. So therefore, I can express my resistance change as a function of the original resistance, the gauge factor of the strain gauge, and the strain that the gauge is experiencing. So I can return to my algebraic expression and substitute this for each of the 4 resistance changes on the 4 arms. And by doing so, I end up with an even longer just algebraic equation. You see now I have strains, I have gauge factors, and I have nominal resistances for each of the 4 resistors on the 4 corners of my Wheatstone bridge. Okay, this is pretty bulky, so we're going to make a normal simplification. And in most cases, we can consider where we use 4 similar strain gauges, and if that's true, then each gauge has the same gauge factor, so all 4 are equal. And each strain gauge is also going to have the same initial resistance, so those 4 resistances are equal. And if we do that, for instance, this quantity would change from R1 over R1 plus R4. It would turn into R over 2R, or 1/2. So we can go through and algebraically simplify this now, and we end up with the change in output voltage divided by the constant input or excitation voltage is equal to, and we have a much similar expression that involves now the gauge factor of our strain gauge and the 4 possible strains that the 4 gauges could see. Okay, so now we know how the 4 arms of the Wheatstone bridge using 4 strain gauges are going to interact to affect the voltage output. So where do we place those 4 strain gauges? Well, it depends on what we want to achieve. The strains that the gauges actually experience or see are functions of 2 things. One would be the location of the strain gauges on the specimen. We could place them in different places and in different orientations. And then also the gauge positions on the Wheatstone bridge circuit. Do we put them on arm 1, 2, 3, or 4? What combinations do we use? Well, depending upon that, we can use this to our advantage to weed out unwanted effects. And the title of this slide shows 2 good ideas: apparent strain and temperature compensation are 2 very good things we could use this for. Let's look at one case, probably the simplest case here, that shows how we can compensate for temperature changes. So let's assume in this situation where we want to measure a mechanically induced strain and we do not want to measure a temperature-induced strain. How can we achieve that in our measurement? We'll come over here to our Wheatstone bridge, and we'll take arm 1 on the Wheatstone bridge, and we will replace it with, we'll call it our active strain gauge. We'll take arm 4 of the Wheatstone bridge, and we will replace that with a identical strain gauge, and we'll make that our compensating gauge. Well, remember there are 2 things we can control: where we place these gauges on the Wheatstone bridge, and then also their orientation on the actual specimens. So let's go over to our specimen. Here's the specimen that we wish to measure. So it can experience a normal force loading, and this gauge will be oriented in that direction to measure that strain. We'll also take another piece of the same material. So same material, and it's nearby, so it's experiencing the same temperature. And we'll call this our compensating block. And we'll lay the compensating strain gauge on it. I have a little typo here. That should not be 2. This is actually this second strain gauge, but it's placed on arm 4 of the Wheatstone bridge. Well, first, let's look at a case where there is no axial loading on the specimen. In that situation, there could be a temperature change, and if there were, we know that the material, the metal, would expand or contract, and that would cause an apparent strain. So we'll say that strain gauge in position 4 would experience a temperature-induced strain, and the strain gauge on position 1 would experience also a temperature-induced strain. In that situation, it turns out the voltage output is 0. Now, how did I get there? So you can look at the previous couple slides here, and I can write out this equation, and hopefully we can understand how we got to this situation. Well, in the numerator, I have 1 plus the gauge factor times the strain, I believe, on arm 1 of the bridge. And in the denominator, I have 2 plus the gauge factor times the strain in arm 1 plus the strain in arm 4. Okay. Also, I have to subtract from that then what could happen on the other two arms of the bridge. So that's 1 plus the gauge factor times the strain in arm 2 of the bridge. There we go. And then divide that by 2 plus the gauge factor multiplied by strain in arm 2 minus the strain in arm 3. There's my chicken scratch. Okay, well, arms 2 and 3 of the Wheatstone bridge are just regular resistors, so there is no strain in those situations. So this goes to 0. Oops. There we go. Okay, 0. And this quantity as well goes to 0. So I'm left with 1/2. Over here, I have the temperature-induced strain, so that becomes temperature-induced strain. And then both of these arms also become temperature-induced strain, so I can replace those. So now I'll have 2 times temperature-induced strain. So let's see. I have 1 plus gauge factor times temperature strain. I have 2 plus 2 times gauge factor temperature strain. In other words, I have 1/2 minus 1/2, 0. So algebraically it all reduces to 0. Now let's look at the second case where I have a mechanical loading occurring. So the normal force is not 0. I have loading. So in that case, the strain gauge on arm 4 is going to experience just possibly temperature or apparent strain. And the strain gauge in arm 1 of the Wheatstone bridge is going to experience the axial mechanical strain plus possibly a temperature-induced apparent strain. Well, in that case, my equation, again, the right-hand side reduces to 1/2. The left-hand side, though, remember, arm 1 is going to have axial and temperature strain. Arm 4 is going to have just temperature strain. Well, if I replace that and reduce, I end up with, in my numerator, the gauge factor times the axial strain. And in my denominator, I end up with 4 plus the gauge factor times 2 times the axial strain plus 4 times the temperature-induced strain. Remember, gauge factors are on the order of 2, and strains are on the order of a microstrain, so 1 times 10 to the negative 6. So consider this. I have 4, and then I have 2 or 4 times 2, so let's say that's 8 most conservatively, times 1 times 10 to the negative 6. So I have 4.000008, let's say. Well, for all intents and purposes, that's just 4. So the only thing that really comes out is the axial induced strain in this case. We have compensated for the temperature. It's been subtracted out through the Wheatstone bridge. So my change in voltage output is now effectively related to the mechanical strain only, not the temperature-induced strain. At this point, we should also mention an important aspect of temperature compensation on the lead wires for a strain gauge. It's actually not recommended to use just 2 wires to connect a strain gauge to a Wheatstone bridge. On the image here on the left, if you use just 2 wires, well, that wire has its own resistance, RL, lead wire resistance. And then this second wire also, if it's the same length and type, has the same lead wire resistance. If you think about it, then this arm of the bridge now looks like 2 times the lead wire resistance plus the resistance of the actual strain gauge. So what would happen is, let's say a temperature change was experienced. Well, it may be not in the strain gauge, but maybe in the wires connecting it. Well, the wires are metal, so they will expand, contract. They'll also have resistance changes due to the temperature. So that will cause an apparent temperature strain. A better way to do this and to connect the wires, this is the reason why you used 3 wires actually in the application video for the strain gauge. So we have this wire connected from one pad of the strain gauge to a power corner. We have one of the 2 wires connected to the signal corner, and we have the other wire connected to arm 4 of the Wheatstone bridge through the strain indicator. Now look at this case. This arm of the Wheatstone bridge has a resistance of RL. This arm of the Wheatstone bridge has a resistance of the dummy resistor plus RL. We just saw on the previous slide how putting a signal on arm 1 and arm 4 at the same time are canceled effectively, subtracted by the bridge equation. So if a temperature change occurs on the wires, this one will have an apparent strain, this one will have an equal apparent strain, and arm 4 and arm 1 will cancel out. The only thing that the bridge will record or see output is the mechanical strain on the strain gauge. So we've effectively now compensated for temperature changes on the connecting lead wires. Now notice this does not compensate for the effect of the lead wire in the first place. So for that we need to make a note here, an important note. So for lead wire compensation, we're going to say see section 4.9 of the indicator manual. Let me dot my I's, cross my T's. If I switch over to the strain indicator manual, remember you can access this from the inventory website. I can scroll down to, I believe that's section 4, which are the operating procedures for a strain gauge. So you go through the setup, the input connections, choosing the bridge type, which we'll discuss in just a moment. Excitation, voltage, gauge factor, zeroing out the amplifier, running it, balancing the bridge. So note section 4.9 here, calibration. This actually allows us to compensate for the lead wire effects. You can see that here. When using the quarter bridge configuration, in other words one strain gauge, the cal position can be used in conjunction with the gauge factor potentiometer to compensate for lead wire resistance. There we go. So that's why section 4.9 is important. By using 3 wires you can compensate for lead wire temperature changes, but you can use this section 4.9 to actually compensate for the effect of resistance on your connecting lead wires in the first place. Okay, I guess as a good salesman I should say, but wait, there's more at this point. We can continue to explore different ways to position gauges and different numbers of gauges on a specimen to compensate for other effects. And I won't read out all of these to you, but we have different cases of a single bridge, the one that we've been using in bending. There's the case of a half Poisson bridge where you have one gauge, arm 1 here axially, arm 2 laterally. We have a half bridge, so again 2 gauges on top and on bottom in bending. On the next page we have the use of 4 gauges, and the whole idea here is that you can compensate for instance, you want to measure tension forces only and not bending. Well, we can choose the orientation and the number of gauges to actually subtract out any bending and magnify any tension, or we can do the reverse. It just depends on the application you need. There's even a torsion situation you can set up for torsion on a beam. I'll go back here and mention this full beam configuration with 4 gauges only because, as the text states, this 4 gauge version is the most popular. It provides a linear bridge output. And we like linear outputs, right? Because we only need a single sensitivity factor to convert from the output to the input, or vice versa. Well, it's this type of configuration, producing a linear output, 4 arms of the Wheatstone bridge, and you might connect this to the load cell that you used in the first big assignment for this class. The load cell had 4 strain gauges connected in a bridge arrangement, and it was done to provide a nice linear output on that beam between the bending of the beam and the voltage output. So hopefully you can see how things have sort of tied together nicely. I should also mention as well, these images I've been using come from the Vichet Experimental Stress Analysis Notebook that were published for students back in the late 80s and early 90s. Moving back to the strain indicator operator's manual, we can see how you can use this to implement the multiple bridge configurations. I will scroll down here back to the operating procedures, and here we are. Section 4.3 is where you select the desired configuration you want. We can have a full bridge using 4 strain gauges, a half bridge using 2 strain gauges, or a quarter bridge using 1 strain gauge. And the next page then shows us how those are to be connected to the strain indicator. We've been using this guy, the quarter bridge with an internal dummy. So hopefully you can see conceptually how this matches the Wheatstone bridge configuration. Here's our active gauge with 1 wire with its resistance connecting to the power corner. We also have the second connecting wire with its resistance, lead wire resistance, connecting to the second or arm 4 on the Wheatstone bridge, and we can connect it here to make that a 120 ohm resistor, which is the same as the 120 ohm strain gauge you're using. Strain gauges also come in 350 ohm varieties, so you have that second option should you need it. And then to mitigate for temperature changes on the lead wire, we have the second wire connecting to the signal corner on the Wheatstone bridge. If you want to use 2 gauges in one of the previous configurations shown to compensate for some unwanted effect, you can do that here in a half bridge with the gauges adjacent or apart depending upon your need. And then if you want to do a full bridge configuration like the load cell you used in the first assignment, well, you can do that here as well. So I believe those are T's for tension, C's for compression in aligning the gauges such that they're used on all 4 arms of the Wheatstone bridge. And in this way we can compensate for multiple things. If you're wanting to use these for any of your senior design projects, you should consider, do you need to compensate for anything as a error control? And if you do, maybe consider one of those configurations. So that ends our discussion on an introduction to strain gauge systems. And now we'll move on to using digital data acquisition through a computer, analog to digital conversion board, and LabVIEW software. And we're going to talk about three sub-subjects. One is our actual National Instruments DAC board that we're using on each computer. We'll tie in what you've been reading about electronic noise reduction in low-level measurements. And then we'll also tie in the assignment you've previously had with creating your first LabVIEW program to measure voltage inputs on a DAC card. So what is the hardware that you're using in this lab? Well, in the KC289 instrumentation lab, each of the 8 computer stations we have has this sort of functional setup. The first thing that you see is the connector block. Okay, ours is a model CB-68LP. Okay, so realize first that this is the connector block. Okay, this is not the DAC. This is not the analog to digital converter system. So I'm going to cross that out. This is a very common misconception. All this is there's no circuitry or electronic circuitry rather to it. It's just a connector pin to take wires from whatever measurement systems you're using and get those to the DAC card on the computer. So this then connects through a nice low noise connector panel into the DAC card. And this DAC card, or analog to digital converter, as we've seen in previous lecture, resides inside the computer in one of the PCI slots of the computer. Accordingly, its model number is the PCI 6221. And that's from National Instruments. That is the analog to digital converter system. And on top of that, we need software then to communicate with it and organize the information. So we connect that then to our computer software, which is the LabVIEW software that we're choosing to use. There are others available. LabVIEW, I think, is pretty much the industry standard, which is why we've been working with that. So you've had already an assignment going through Chapter 1 of Learn LabVIEW Fast. So you've become a little bit proficient at getting software-timed information off of a DAC card. Let's look a little bit more at the DAC card here. What it does, remember, is it takes an electronic voltage measurement. So it takes an electronic voltage measurement. If it does that, remember our, I believe, second lecture of the course was introducing ourselves to this entire process of taking an analog voltage signal and turning that into a digital electronic measurement. That is a transducer, so accordingly it thus has a resolution. So it has a resolution, and it also has accuracy. So if we are going to measure anything with this system, our instrument that connects to the connector block might have its own accuracy information, which leads to an uncertainty measurement or error estimation. Well, our analog to digital converter system is also going to have uncertainty due to its errors and resolution. So let's take a look at a little bit more at that. You can use the course website as a link to the National Instruments PCI 6221 DAC card specs. So we can follow that link, and that brings us to the National Instruments website. And that shows the DAC card, low-cost series multifunction data acquisition. We can see, remember, we talked about how many bits the converter has in being important in its resolution. So this is a pretty high 16-bit card. The number of samples it can take per second. We saw, well, the card is actually capable of 250,000 samples per second. And however, that is the hardware timed. Your first assignment with LabVIEW was using the computer as the timing system. So we were able to achieve much smaller measurement speeds using the computer processor. And the further chapters of Learn LabVIEW Fast can help you exploit this for hardware timing. We also see that we have 16, 32, or 80 analog inputs. We'll talk about that a little bit later. This card is actually also capable of giving out analog outputs, and it can also give digital output as well, ones and zeros essentially. And remember, for the resolution there are two important things. One is the voltage range that you're dividing. The other is the number of bits you can use to hold that digital information. Well, this card you can program into 4 ranges. It can measure its highest resolution over a 200 to negative 200 millivolt voltage range. So if you're using, for instance, a strain measurement from a Wheatstone bridge, it's probably going to be a very low signal. You'd want to use the lowest voltage range to get the highest resolution. We can also choose a plus or minus 1 volt range, a plus or minus 5 volt range, or a plus and minus 10 volt range for the card. Now let's scroll down on this website. There we go. Okay, we're looking at the section on calibration for the analog input, which is what we want. Now realize here are our 4 voltage ranges that we can select in LabVIEW. So here's a 400 millivolt full-scale range, a 2 volt full-scale range, 10 volt, and 20 volt. There are many different error sources. There's a residual gain error, a temperature coefficient on the card as well. There's the reference coefficient. There's offset residual, so that might be related to 0 offset, for instance, and that also has a temperature effect. Here's random noise, so that would look like repeatability in our instrument calibration. And then on top of all of this, we also have the resolution. You know, this would be 20 volts divided by 2 raised to the 16 power to get the resolution of the card in that program. Well, you don't have to combine all these. They've already been combined for you, and then this is the column you want to focus on. The absolute accuracy at full scale. So when you're using the PCI 6221 DAC card and you want to incorporate its accuracy into your uncertainty calculations, if you're using a plus minus 10 volt channel, you're going to have plus or minus, 3 millivolts for your accuracy. A plus or minus 5 volt channel is going to give you about 2 millivolts. Here you have 0.3 millivolts for the plus or minus 1 volt channel, and the best accuracy we can get is for a plus minus 200 millivolt range, giving us 0.1 millivolt absolute accuracy. Hopefully you can see how that ties in then to lecture 2 and what we've been learning about uncertainty. So we've covered now the hardware that the computer is using and the errors associated with that as it turns an analog input voltage into a digital computer memory. We also have to consider how we're connecting the instrument to the DAC card and the types of error that can come in through that. Essentially, we're talking about electronic noise. So I have the reference here. You have as an assignment reading pages 19 through 23 of the Omega manual on analog data. Well, that manual says that noise is defined as any unwanted electromagnetic phenomena that can corrupt a message signal. So if you're planning to send a steady voltage signal, maybe through a battery, for instance, as we saw in class with the LabVIEW. Well, so that's time and this is voltage. You might be expecting a steady signal. Well, instead, we have these electromagnetic effects, essentially the connecting wires acting like antennas almost. And that results then, instead of your nominal voltage, you do have that, but you have a error on top of it. And there's the noise on top of the signal. You probably noticed that as you were testing your first LabVIEW program. Well, the effects of that noise can be reduced through engineering design, installation, routing of the wires and cables, and shielding and grounding. The lowest hanging fruit, I think the easiest thing for us to look at, is the shielding and grounding. And as you'll see in that reading, there are 3 types of shielding that are fairly easy for us to do to try to reduce noise in a signal. We'll never remove all the noise, but we can do 3 different things. And these are increasing usefulness and increasing cost. So the easiest thing, if you have 2 plain wires, twist them in regular intervals. By twisting them together, you're going to, I believe, cancel out any sort of antenna effects on the wires. The next thing we can do is use a wire that also has a shield in it. If you remember using the load cells, note that there were 4 color-coded wires. The black and red for the excitation voltage, the green and white for the output signal voltage, and then there was a bare wire also. Well, those were actually shielded together, and that bare wire could be grounded, ground that shield, that bare wire, at the source of the signal. So we could have done that to try to reduce noise on the load cell. And then the coaxial cable, like an old cable system, you use those actually when we, you've probably used those in electrical engineering classes. Those are already grounded, not affected by any external electromagnetic effects. So here's the cost, increased in cost with those different techniques. Next, you'll see you also have a reading assignment from a National Instruments document. I have the link down there, and the formal link is on the course website, talking about other noise reduction techniques. And one thing to focus on there is grounding. And that document says, in general, you want to use a differential measurement system. That is the one that you were using in your first Learn LabVIEW Fast assignment. You were taking differential measurements. It's preferable because it rejects ground loop errors and also noise picked up. If any noise is picked up on both wires, then by using a differential measurement, you're subtracting that out, and you keep the signal that you want. Opposite to that, you have floating or non-referenced signals that you're going to read about, and those actually need extra bias resistors. As you're doing your reading, you can focus on this table from the National Instruments document, and it has a nice sort of comparison between the two. So our grounded signal source, we want to use a differential measurement, and let's see here. If this is our instrument, then we have analog input positive and negative. The DAC card is grounded, and then we also want to ground the signal source as well. Also, we have floating signal sources not connecting to the building ground. Your load cell would be an example. Thermocouples would be another example. Anything that's powered by batteries instead of having to be plugged into the wall, those are other examples of things that are floating, not connecting to the ground of the building. So in this case, you see your measurement device, and we have ground here, but note that the ground is not connected to the device at all. So it's not grounded. We have our digital conversion system, and we have analog input on the positive side and analog input on the negative side. And what we want to do is take two resistors, somewhere between 10 kiloohms and 100 kiloohms, just pick two of the same value, and connect one to the positive, to the ground, and the one on the negative wire, connect it to ground as well. And what that does is, if it's floating, it has the possibility of picking up a stray voltage that then sort of saturates or overwhelms the signal. And if you've set your DAC card, for instance, to measure plus or minus 1 volt, you might see it suddenly saturate at positive 1 volt or negative 1 volt. That's a classic case of this floating signal source. The way to fix that is to provide a way for that spurious voltage to dissipate to ground. That takes away that offset and allows you to recuperate your actual measurement signal that you want. I know this is, we're mechanical engineers, and all of this electronic stuff is sometimes more complicated for us. So what we're doing is you have your reading assignment where you can print out these documents, take notes. I've provided 2 highlights here from both of those documents, and then when we come into class on Thursday, you'll actually do a couple of hands-on lab practices where you explore these different signal noise circumstances. Finally, we have just a review here of what you accomplished with your assignment to work through the first chapter of Learn LabVIEW Fast. Realize that you accomplished software-timed analog input, so we were limited at the rate of data we could take through the CPU clock of the desktop computer. You also learned to acquire a finite set of measurements or to acquire measurements continuously. I'll come down here in one page so we can see this sort of zoomed in. If I use a program flowchart to sort of see what you did, the first thing you did was use a select case feature or a switch to choose whether you wanted to run in finite mode or in continuous mode. If you wanted to run in finite mode, you required the user to input the data, the sample rate, the number of samples you wanted to take as well, and the file name, and then you actually went into a for loop. So for however many numbers of samples you wanted, you looped through, measuring the voltage, outputting it, pausing for some period of time, and then looping back through, doing that n number of times until you finally exited the loop, outputted with a final graph, and then ended the program. If you instead chose to do a continuous data collection, so you switched to continuous, then you had sample data input, the file name as well. You then went into a while loop where you measured the voltage, outputted it on a chart graph. You checked to see if the stop button had been pressed. If it did not, then you paused for the amount of wait time you specified at the beginning, and then you continued to loop back through. And the only thing that would stop that would be pressing the stop button. Once the stop button was pressed, it would take one more measurement and then exit out of the loop, output the final summary graph, and then end. So all these things come together nicely. In your next assignment, as you're going to see, you're going to use your LabVIEW programming skills. You're also going to use the Lecture 2 material we learned on digital data acquisition. And you're also going to use your strain gauge system. You're going to build your own Wheatstone bridge, and instead of using the strain indicator to condition and amplify that signal, you're going to use LabVIEW to measure that analog voltage output from the Wheatstone bridge. convert that to a digital signal, and then measure that and treat that so that you can actually calculate the strain. And hopefully that'll provide a wonderful opportunity to synthesize the separate topics you've been learning these past 5 weeks in the course.